Hello and welcome to the chapter 13.5 lecture on lines and planes. So to cleanly express lines in three-dimensional space, what we want is a parametric equation. A parametric equation is an equation in terms of what we call a parameter. Typically, we use the letter t for that parameter. And that letter t, as it varies, it will give us different points on that line. And the vector equation of a line through a point r0 in a direction v is r of t is r0 plus tb. So visualize that with this diagram. So here's our initial point r0. The textbook calls it p0 in this diagram. And then we can move from there in a direction v, and t is a scalar. And the larger t is, then the further we go along the line. And when t is negative, then we go along the line in the negative direction. So every point on this line corresponds to this equation for some given point t, where that t is just how much we need to scale v to get to that point. And this parametric equation can be broken down into its components. So this is the form that we were just presented. This is our r of t is equal to r0 plus tv. And this form just has the components of each vector spelled out. And this is equivalent to this parametric equation of the line. It's two equivalent forms of the same parametric equation of the line. And this comes from just writing out the individual components. So for example, x must be equal to x0 plus t times a. And all of that corresponds to that. It's just setting the first components on both sides equal to each other. And likewise for the y and z. And the distance from a point to a line, we can use our cross product and some clever reasoning to find a very slick equation for this. So to find the distance from a point Q to a given line, what we can do is choose any point on that line. And we can get that random point by just plugging in a random t, since every point on the line is given by some t. So for example, we can just plug in t equals 0 is usually the easiest choice. And now we know that v cross pq is by definition, in magnitude, is by definition of the cross product equal to the magnitude of v times the magnitude of pq times sine of theta, as illustrated here. Recall that from the chapter 13.4 lecture. But pq times sine of theta is by trigonometry equal to that distance to the line, because that's the right angle. And if we had any other point on the line that we were going to, like that, then that distance would be longer by the triangle inequality. That's the hypotenuse of a triangle with right angles, so that distance would be longer. So the point on the line that's closest to Q is necessarily a point that forms a right angle with the line from Q to that point. So anyway, that means it's the opposite side of this right triangle, which is PQ, the hypotenuse, times sine of theta, which is a component of the definition of the magnitude of the cross product. So therefore, the magnitude of B cross PQ is equal to the magnitude of B times this, and that is D. So let me just take both sides of this equation and divide by the magnitude of V, and we get that the distance from a point Q to a line is V cross PQ over the magnitude of, in magnitude over the magnitude of V, where again, P is just any point on the line, which we can obtain by, for example, plugging in T equals 0. So that's a nifty and slick equation and a nice application of the cross product. So let's do an example. Let's find the distance from the point 1, 1, 1 to this line. R of t is 2, 1, negative 1 plus t, 1, 2, 3. So first we need a point P on the line and a point P on this line is R of 0. Again, we could choose any t. Since any t will output a point on the line, but 0 is the nicest choice, which is 2, 1, negative 1 plus 0 times 1, 2, 3, which is 2, 1, negative 1. And we actually could have known that a priori because our definition of the line is a point on the line plus t times a vector in the direction in which the line goes. So this point here is always a point on the line. So now we need to find the cross product of v and pq. So that is 1, 2, 3 cross 1, 0, negative 2, which is the determinant of the matrix 1, 2, 3, 1, 0, negative 2, ijk per 13.4. And expanding along the last row, that is the determinant of 2, 3, 0, negative 2, I. So if all of this looks unfamiliar, I recommend that you review or look at my 13.4 lecture on the cross product. So this is the submatrix obtained by deleting the row and column in which I reside, so 2, 3, 0, minus 2. And then we have a minus sign by the j. And deleting the row and column in which j resides, we have 1, 3, 1, negative 2. And then plus 1, 2, 1, 0, k. Again, deleting the row and column in which k resides, we're left with 1, 2, 1, 0. Okay, now the determinant of a 2 by 2 is the product of the main diagonal minus the product of the other diagonal. So that's 2 times negative 2 minus 3 times 0, I, minus 1 times negative 2 minus 3 times 1, j, plus 1 times 0 minus 2 times 1, k. Okay, so that is negative 4i plus 5j minus 2k. Or in our other notation, negative 4, comma 5, comma minus 2. Okay, so we now just need to take the absolute value of that, finish plugging it into this formula, and we'll be done. Okay, so this guy is the magnitude of negative 4, 5, minus 2. Over the magnitude of 1, 2, 3. So that is the square root of negative 4 squared plus 5 squared plus negative 2 squared, all over square root of 1 squared plus 2 squared plus 3 squared was square root of 14. And we are done. That's the answer. And that cannot be simplified. Okay, that's just two equivalent ways of expressing it. Yeah, and again, this formula came from taking V cross Q over the magnitude of V. and v cross q, remember, was of magnitude of v times, well, this length, giving the area of the corresponding parallelogram. So then divide by this and we're left with just the distance. I think it's important to geometrically understand where these formulas come from. So that covers lines, equations of lines, distances from a point to a line. And now we need to talk about planes. Later in this course, we'll be talking about tangent planes to a surface, just as in Calculus 1, you talked about tangent lines to a function. So first definition, the normal vector to a plane is a vector that is orthogonal to the plane. So visually here is a plane, two-dimensional flat surface, and the normal vector for this plane is this. A normal vector for this plane is this, which forms a right angle with the plane, no matter which direction we face on the plane. And notice that it says a normal vector, because there are many normal vectors. We could stretch this to be twice as long, and that's still a normal vector. And a plane is completely determined by a normal vector n to the plane and a point on the plane, which we'll call p naught. And you can visually see that. So given a point on the plane could swing around however it wants on that, so long as it has that point. But when we specify a normal vector to the plane, this plane can no longer swing in any way, and the plane is uniquely specified. So if a plane is uniquely determined by a normal vector to it and a point on the plane, we should be able to find an equation for the plane in terms of these two guys. And how can we do that? Well, notice that the normal vector defines the plane by specifying that every point on the plane is such that the vector going from our chosen point to that point is at a right angle to the normal vector. And we have something that is always zero when the two vectors are at a right angle, and that's the dot product. So we can specify the plane by specifying that the dot product of n and every point p naught p is equal to 0. Remember that the dot product is 0 if and only if the two vectors are orthogonal. So in other words, the equation of a plane depicted on the left here is the dot product of the normal vector and p naught p, where p is any other point on the plane. And we can expand this out and get an actual equation in terms of x, y, and z. Well, this is an actual equation, but get a more standard-looking equation that we might be more comfortable with. So expanding this out in terms of the constituent components of the normal vector and p naught and p, we know that the normal vector has components a, b, and c, and p naught is our point x naught, y naught, z naught. And p is our point x, y, z. So this is x, y, z minus x naught, y naught, z naught. And that is this. And then taking the dot product, so a times this is that, plus b times that, and so on. And the two are orthogonal, so their dot product must be 0. So thus we have the equation of a line through a given point, a x naught, y naught, z naught, with normal vector a, b, c. And this is called the point normal equation of the line, because it's the equation of a line given a point and the normal vector. Okay, sometimes though we want to find the equation of a plane through 3 points. And this is a bit more challenging because given 3 points, we don't know immediately a normal vector, we're not told it. However, as you can visualize 3 points uniquely determine a plane, just as 2 points uniquely determine a line. So how do we find a normal vector to this plane? Well, let's visualize this situation. So here's our point P, Q, and R, as we'll call them. And here's a visualization. There's P, Q, and R. And we want a normal vector to it. Well, this normal vector is by definition orthogonal to the plane, which means orthogonal to every vector spanning from a given point on the plane outward. So what we want is something orthogonal to these two vectors being PQ and PR. That's PR there, and that's the vector PQ. And how do we find a vector orthogonal to two other vectors? Well, the cross product. We know that the cross product of two vectors is orthogonal to both. So therefore, the anormal vector is the cross product of those two guys. Okay, so let's find these two guys. So PQ, that is 1, 4, 0, minus 2, minus 1, 3, which is minus 1, 5, minus 3. And PR is R minus P, is 0, minus 1, 5, minus 2, minus 1, 3, is minus 2, 0, 2. So therefore, a normal vector to the plane is the cross product of these two vectors. Okay, and that cross product is using our standard definition of the determinant. We stick these in this matrix and take the standard definition of the cross product. We stick these in this matrix and take the determinant. And expanding, that is 5 minus 3, 0, 2, I minus 1 minus 3, minus 2, 2, J, plus minus 1, 5, minus 2, 0, K. We just clearly separate those. Yeah, so again, each of these is the submatrix obtained by deleting the row and column in which I, J, and K reside respectively. Okay, and determine if a 2 by 2 is the main diagonal minus the other diagonal. So that's 5 times 2 minus negative 3 times 0, I minus 1 times 2 minus negative 3 times negative 2, J, plus negative 1 times 0 minus 5 times negative 2, K. And that is 10I minus 3J. Oh, pardon me. Triple negative here. So that's negative 2 minus 6 is negative 8. And then another negative is plus 8J. And then plus 10K. Okay, so we now have a normal vector to the plane. So we know that a normal vector to this plane is 10, 8, 10. And we can choose any one of these points to be our point Q, point P on the line. That can be our P naught. So we just plug that in into our point normal form. And we have our equation of the plane. And we can divide both sides by 2 if we want. It's the same thing as 5 times x minus 2 plus 4 times y plus 1 plus 5 times z minus 3 equals 0. And I want to point out that this division by 2 corresponds to that another normal vector to the plane is 5, 4, 5, which is just this guy divided by 2. And that's because if you take a normal vector and scale it, it's still going to be orthogonal to the plane. Okay, so that's equations of planes and how to find equations of planes. Now a couple definitions. 2 planes are called parallel if their normal vectors are parallel, as you can visualize here. And 2 vectors are called orthogonal, meaning they always intersect at a right angle, if their normal vectors are orthogonal. So this is a slick way of, well, finding if planes are parallel or orthogonal. You just look at their normal vectors and ask the same question of them. And remember that 2 vectors are orthogonal if and only if their dot product is 0. So let's do an example. Let's determine if these 2 planes are parallel, orthogonal, or neither. So for this first plane, we can just look at the coefficients and gather from that the normal vector. I know that the point normal form of a plane has our x minus x naught, but we can just move that to the other side and it doesn't change the coefficients. I mean, we can move the x naught, y naught, and any scalar multiples of them to the other side, and the coefficients of x, y, and z are still the components a, b, and c of the normal vector. So the normal vector here is 1, 2, minus 3, and the normal vector here is 4, 1, 2. And I know I keep habitually saying the normal vector. Again, you should keep in mind it's a normal vector, but still. Okay, so are these 2 scalar multiples of each other? Let's call these n naught and n1. So we know that n naught and n1 are not parallel because they are not scalar multiples of each other. And a way to quickly see that is that the only way they can be scalar multiples, the only way that n1 can be c times n naught is if, well, we multiply n naught and get n1. So that would mean that our scalar would have to be 4 in this case, because 4 times 1 is 4, only way to scale this first vector and get the second, but 4 times 2 is not 1. So the only possible choice of our scalar here to get this vector is 4, and that doesn't work. So now let's ask, are they orthogonal? Well, then n naught dot n1 would be equal to 0. We're asking that as a question. Let's see. So is it the case that 1, 2 minus 3 dot 4, 1, 2 equals 0? Well, this dot product is 4 plus 2 is 6 minus 6. So indeed, that left side is 0 and the right side is 0. That's a check mark. And they are therefore orthogonal. Okay, so those two planes are orthogonal because their normal vectors are orthogonal. So those two planes look like this. Now, sometimes we're given two planes and we want to find their line of intersection. The line of intersection in this case, for example, being this. So how do we find the line of intersection of two planes? Well, first we want to express lines in 3D space in parametric form. So that involves that parameter t. So we know that a line in parametric form is r of t is a point r naught plus t times v naught. And that means that we need a t. And here's a key insight. The scalar t can be any one of the variables. So the parameter t can be x, y, or z, or anything else for that matter. I'll just say etc. It could be 2x plus 3z, any linear combination of them. So that means that we can just rename one of them, say z, to now be called t. And a way to visualize this is that, let me draw a little 3D space here. Okay, so here is our x, y, and z. And we have some line. Okay. Do my best to make that look like a line in 3 dimensions. And if we call z t, then that means that for each point t, we get a different point on the line. So imagine a sliding scale here on the z-axis. And as we slide up the z-axis, then we get different points on the line. So that means that our z is the parameter t, different values of which give different points on the line. So we can do this by, well, doing that. Let's rename z to t using this visualization. And then we'll try to get everything in terms of t alone. So what we want is x, y, and z, each in terms of t alone. So in other words, we want x to be equal to some expression with only t and scalars, numbers. So what we want to do, therefore, is eliminate this y from x. And how can we eliminate y from this equation? Well, we have another equation for y that is in terms of just x and t alone. So we could, for example, well, not for example, we're going to do this. We can just plug in the second equation, y equals x plus 2t plus 2. Okay, so now that guy is going in for y, and we get x is 2 times x plus 2t plus 2 plus t plus 1. And now we just move this x to the other side, and we'll have x in terms of t only. So we had x is 2 times x plus 2t plus 2 plus t plus 1. And expanding that, we have this. And then moving x to the other side, we have this. And therefore, x is -5 minus 5t. Oh, and that looks an awful lot like a component of a parametric form. That's like the x part, and then a part of the scalar v, part of the vector v times t. And now we want to do the same thing to y. So now y is x plus 2z 2t. We renamed c to t plus 2. And this whole guy is x. So we can just put that there, and we get y in terms of t only. Now, lastly, you may be wondering, how do we get z in terms of t? What is z in terms of t? Well, z is t. It's that simple. Since z is t. So we now have our parametric form in terms of the individual components, x, y, and z. And now we may wish to convert this into a more standard vector form. I need to go to the next slide here. No, next slide. Okay, well, our insight to convert it to a more standard parametric form is that this t by itself is the same as 0 plus t. So now our vector x, y, z is equal to, just setting the components equal to -5 minus 5t, comma, -3 minus 3t, comma, 0 plus t. And now we separate this into the components. So let's call this guy an arbitrary point on the line. We'll call that our r of t. And expressing this as a vector sum, we can pull out the constants. That's -5, comma, -3, comma, 0, plus -5, comma, -3, comma, 1, t. So that is a r naught, as we called it, plus a v t. So that is the parametric equation of the line that is the intersection of these two planes. I know that's a lot of steps, but the recap is we can just rename one of the variables to t per this visualization. So here when z is t, different points on the t-axis now correspond to different points on the line. And then we want to get x and y each in terms of t alone. We can do that by substitution or elimination. And then whichever variable we rename to t, it is just t. So then we have each x, y, and z in terms of t only. And then we write this system of equalities as an equality of two vectors. So x is equal to 5 minus 5t, the first component, and so on. And this x, y, and z is our arbitrary point on the line. And then we can separate this as a vector sum and product in this way. And if you're confused about this last step, I encourage you to just compute this. So the t multiplication, that's a scalar, it distributes to each of these components. And then when we add them, we get that. Here's another example. And fortunately, in this case, it's a bit simpler because we won't need to do substitution. So this is kind of have to illustrate that sometimes this process doesn't involve so many steps. So in what vector does their line of intersection face? So we'll do the same thing. We'll just rename z to t. Again, you could rename x to t or y to t. It doesn't matter in most cases. And when I say in most cases, in some cases, it may be the case that, for example, the line is orthogonal to one of the axes. So for example, if the line is orthogonal to the x-axis, then as you vary x, you can't get to different points on the line because there's only one x that is everywhere on the line. But in most cases and in all cases where the line is skewed to all three axes, then you can choose any one. So we'll rename z to t. We get this. And let's include our final z. We rename z to t, so that's just that. Okay, so now we have x is 5/3 plus 1/3 t, y is 1/3 plus 2/3 t, and z is still just t. And we'll put a 0 there, and now we have that setting, expressing this as a vector equation, x, y, z is all of this. So x is that, the y component is that, and the z component is this. So that is our r equals 5/3, 1/3, 0, plus 1/3, 2/3, 1 t, and this is our r0 plus d t, and the v is the direction of the line. So therefore our answer is 1/3, 2/3, 1 is the direction of the line of intersection. And if we don't like fractions, and I do not, then we can take this and scale it. We can scale it specifically by 3 to eliminate the fractions. And it becomes 1, 2, 3. Okay, and what exactly did we do here? Well, if we have a line and we have a vector v in that same direction, then 3v is still in that same direction. So, and it comes back to the more general principle that as far as directions are concerned, you can always scale the vector and it's still in the same direction, just geometrically. So either one of these is acceptable answers alongside infinitely many more, namely every scalar multiple of this vector, aside from 0, since 0 is just a point. And now our last topic is the distance from a point to a plane. So earlier we found the equation for the distance from a point to a line, and that involved the cross product. And ironically, the equation for the distance from a point to a plane will be simpler to compute than the distance from a point to a line. So given a plane, ax plus by plus cz equals d, and a normal vector to the plane, abc, we can let q be a point on the plane. Let's visualize this as we go. So let's imagine that this is our plane. I know it looks like a line. This is a plane, though. Just imagine that it's coming out of view from the screen that you're looking at. And we have a point Q on the plane. And we have a point P that is not on the plane. what is the distance from P to the plane? Well, let's imagine the normal vector. A normal vector. There is a normal vector n to the plane, forming, as always, right angles. And let's imagine the line PQ. If we orthogonally project PQ onto n, then we get this. That length, so the orthogonal projection of PQ onto n, since this is a right angle there, will be this vector, oriented technically going downward. But when we take the magnitude, that doesn't matter. So that guy is the projection of PQ onto n. In magnitude. And it's really just that. And at this point, it's just a matter of, similar to some previous things that we did, like finding the equation of a plane, the point normal form. We just want to expand and simplify this to get it into ABC, to get in terms of ABC in our point Q. So you may be wondering, wait, why couldn't we do this for lines and avoid the cross product? Well, there is no such thing as a normal vector to a line that is unique up to scalar multiples. So in other words, we don't know a priori onto kind of which normal vector to the line to project. But because planes have a unique normal vector up to scalar multiplication, we know onto what to project. So that means that this guy avoids the cross product, and that is what will fundamentally make it easier to compute than the distance from a point to a line. Okay, so now let's expand this in terms of ABC and Q. So assuming that C here is not equal to 0, and if it is 0, then we do the same thing, but for A or B, one of these coefficients must be non-zero. And that's because if they're all 0, then we would have 0 equals D, and the only way that can be true is if D is 0, so then we have 0 equals 0, and that's not a plane at all. So if this is a plane, one of these guys must be non-zero. So let's assume, without loss of generality, that it's C. And then plugging in x equals y equals 0 into this and solving for z. Well, if x and y are 0, then z is just d divided by c. So this is therefore a point on the plane. And we just need a point on the plane. It doesn't matter really what this q is, so long as it's on the plane. Now we can find a point on the plane by just finding any point at all that satisfies this equation for the plane. And 0, 0, d over c satisfies that equation. So let's use that as q. And the normal vector corresponding to this equation is, as we've learned, ABC, just the coefficients of x, y, and z. And let's call our point P, from which we want to find the distance to the plane, x naught, y naught, z naught. And we know that this is a point on the plane. So then PQ is just the difference of these two points regarded as vectors. So we have x naught minus 0, y naught minus 0, z naught minus d over c is that. So we know that the distance from the point to the plane is the projection of PQ onto the normal vector. And at this point, we use that formula that we derived for the projection. So for this, review chapter 13.3, if this is unfamiliar, but this is plugging into the formula that we derived in 13.3 for the orthogonal projection. So we have PQ dot n over n dot n times the vector n. This whole guy right here is just a scalar. So we can pull it out by the fact that a scalar c times a vector in magnitude is the magnitude of c times the magnitude of v by properties of magnitudes that we learned earlier, and also intuitively. C just stretches it by a factor of c, but c could be negative, so we need to put absolute value signs around it. So we can pull out that scalar in its own absolute values, and then times the absolute value of our normal vector n. And then finally, going from here to here, that is because the magnitude of n over the absolute value of the absolute value of n squared absolute value. Okay, well, the absolute value of the absolute value is just the absolute value. So we have n over the magnitude of n squared, and that is just 1 over the magnitude of n. So in other words, that and that cancel out effectively, and we're left with just the magnitude of PQ dot n over the magnitude of n. So now finally plugging in the points, well, our point Q that we have found, an arbitrary point, and PQ, and n being a, b, c. So PQ is this, n is that, and we take the dot product, and we have a times x naught plus b times y naught plus c times z minus d naught, and that product is this. So the magnitude of that over the square root of a squared plus b squared plus c squared. So this is our formula for the distance from a point x naught, y naught, z naught to the plane with ax plus by plus cz is d. You can see it doesn't have a cross product, and it's not bad to compute at all. And we really could not have found this, at least not at all nicely, without our knowledge of vector algebra. Okay, so applying this is really just a matter of plugging in, but maybe we should do that anyway, just to be clear. So let's find the distance from the point 1, 2, 3 to this plane. Okay, so that's our x naught, y naught, z naught. And we have from this that our normal vector is 2, minus 3, 1. And up here, I have just rewritten the formula that we want to plug into, distance from a point to a plane. So the distance is the absolute value of a times x naught plus b times y naught plus c times z naught minus d, all over the square root of a squared plus b squared plus c squared. Okay, so that is the absolute value of 2 minus 6 plus 3 minus 1 is negative 2. All over, so this square root, that's 4 plus 9 plus 1 is root 14. And the absolute value of negative 2 is, of course, 2. So we have 2 over root 14. Or it's more standard to write it this way. So that's root 14 over 7. And if you're a bit rusty here, perhaps I should explain this step. So that is because 1 over root 14, we can multiply that by root 14 over root 14, because that guy is just equal to 1, so it doesn't change anything. And that is root 14 over root 14 squared. And root 14 squared is 14. So we can always do this with a division by a radical and simplify it so that the radical is in the numerator. So that wraps up our chapter 13.5 lecture. Have a good one.